Okay guys, well, welcome to our 6th lecture. This is going to be about stochastic integrals. Not just the Itô integral, but also different integrals as well. So for comparison, and for comparing reasons, I'm going to introduce you to the Riemann integral again. This is what you probably learned at school. And I'm going to extend this a little bit to the Riemann-Stieltjes integral, which is going to be also an interesting one. Again, and later on I'm going to do this in the context of stochastic integrals. But before I do so, before I transition to stochastic integrals, I would like you to reconsider at least the Riemann integral and also in extension to that, the Riemann-Stieltjes integral. Now I'm going to look at total variations and quadratic variations, which is some sort of an integral if you ask. I'm going to define those and examine what kind of properties they have, and these are going to be playing a huge role for stochastic processes. So then, of course, I will look at the total variation of stochastic processes and the quadratic variations of stochastic processes. We're going to look at then afterwards stochastic Riemann integrals and stochastic Riemann-Stieltjes integrals, and as they are basically their stochastic counterparts of the regular ones. And then I'm going to introduce you to the Itô as well as the Stratonovich integrals. Now, the Itô integral is more common in finance, so we're going to basically look at that further, but that will be a topic of another lecture. So that will be just, looking at some sort of limits. Keep in mind that stochastic integrals are random variables themselves. So you should basically understand them in terms of a random variable. But before I do so, I'm going to look at the Riemann integral again. This is the classical one that you probably heard at school or basically some undergraduate studies. When you look at the Riemann integral, it always starts with the partition. So you always have actually an interval. Based on that, I'm going to split just an interval into multiple parts. So S0, S1, and so on are going to be those points where you split the interval. I'm going to basically just illustrate that. Usually a partition is a set of those points, but we're just going to look at that as a sequence. So that will be actually a partition. And there is an interval which actually starts at A, and then basically there is always going to be a closed one without loss of generality in this case. So those lower and upper limits are going to be finite. And this means the following. So you have basically a partition, and then you have actually basically the lower endpoint to be equal to S0 and the upper endpoint to be equal to Sn, and then you have all those points between. So keep in mind, guys, this is a strictly decreasing sequence if you like, okay? And A, of course, is also strictly less than B, because otherwise it would not make any sense though. Okay, so then you have those endpoints. So you should basically think of an interval that you split into n parts, if I'm not mistaken, and those are going to be those points. So here you have S1, S2, and so on, and this is going to be Sn. So you create technically some sort of subintervals, and they don't need to be actually equidistant. So the length of these intervals don't need to be basically the same, actually. Anyways, so this is where you would start. And then you would define the integral, which is the classical Riemann integral, as a limit of the following sum. So keep in mind, guys, you should be, when integrals are introduced, there is always the association related to areas, which is not necessarily true. So you can basically interpret that to be the area of the function from A to B, which is not wrong. But actually, you should be more general than that. So this is always, and that's always going to be some sort of limit of a function, or some limit of a sum, basically where the function is involved that is part of the integrator. So you go from 1 to n, of course, and then you go through that partition. Okay, so keep in mind there is going to be an index. So you're indexing basically the sets here, or the points here from the partition, from 1 to n. And then you calculate the function at point S asterisk, okay, so which is going to be a specific point. That is going to be a point between Si and Si minus 1. You can choose basically which point you want. It doesn't really matter when the limit is supposed to be finite. So if the limit exists, then it doesn't really matter. which will not be the case for the stochastic counterpart. So keep that in mind when you basically look at that. In this case, this point can be anything from Si minus 1 to Si, all right? But again, so if it can be anything, that the limit is basically going to be finite, and there is always going to be just one. Okay, so Si is the upper endpoint of that subinterval, and then you have Si minus 1 to be the lower endpoint of that subinterval from that partition, and Si asterisk is going to be some point between the two. Okay, so you simply see that these are going to be, let's say, the increments here of, that's going to be the time axis, so you can simply just define to be using that for the difference separator. And then you have basically Si minus 1 to be the lower endpoint and Si to be the upper endpoint, and Si asterisk is some point basically between the two. And that's it. And if that limit is finite, then the limit is basically referred to the integral of the function f from a to b. And that's it. And s is going to be called the integrator. I'm not supposed to call it x, as you basically had it somewhere. Okay, so you always write x to be the integrator. I basically used to write s to be the integrator because I'm introducing stochastic processes to be integrators, and then you mix up the two, and that's just simply this is something that I don't want to. Okay, but that, keep in mind, this is just a symbolic notation here for that limit of that sum. So every integral is going to be a specific limit of a specific sum, and to which basically I'm referring to. You can associate that to be the area, actually, of the function f between a and b. Now, the fundamental theorem of calculus yields the following, and this is actually what you're familiar with, FTC, okay? So fundamental theorem of calculus, and it yields that this limit can be computed, okay? So you can simply just bypass, if under a certain circumstance, of course, so it's not always possible to do it, but let's say under certain circumstances, you could bypass by simply taking the antiderivative of the function small f at point B, and then subtracting basically the antiderivative of the function at point A. So you simply just create basically the difference. I think you're familiar with that, right? So you had a simple integral calculus. And yeah, so this is basically what you would do. Of course, that function needs to exist. So that needs to be, among others, it is, sometimes it's not even differentiable. So that function is not necessarily differentiable in that case. Okay, not even continuous, by the way. But again, so I'm not going to discuss basically the properties for which that integral can be calculated like this. But you should keep in mind that the derivative of the function capital F is going to be equal to the function small f. So that at least that derivative needs to exist. And this is basically what you would have, all right? Now, it can be the case that this function is not differentiable at some points, but one of the conditions that must be basically true, if this is actually the case, is that the function capital F needs to be differentiable almost everywhere. So there can be some countable many points at which the function is not differentiable. Think about it, for example, the cumulative distribution function of, let's say, of the uniform distribution is not a differentiable function, but it's going to be differentiable almost everywhere. So that means that basically this is what it's going to be like. Anyways, okay, so that's number one, but I'm not going to discuss Riemann integrals here. Number two, we're going to consider, there is one property which is actually true. So if the function is bounded, and then it is Riemann integrable, that's a term. So Riemann integral means that the limit is finite, which means that it exists. And it's unique in that sense that it doesn't matter what kind of point you choose between the two endpoints of the subinterval I. Now the function is Riemann integrable on that interval actually, if and only if, for example, it is continuous almost everywhere. That is one issue. So it does not need to be continuous, but it needs to be continuous almost everywhere. Remember the term almost everywhere? Almost everywhere means that there can be points for which that it is not true. However, the set of those points for which is not true must be a countable set, because every countable set has the measure 0 when it comes to the length function. I was talking about that back then. It probably was lecture 2 or 3 I can't recall it correctly, but one of the lectures basically was explaining that. Okay, so it needs to be continuous almost everywhere, which means that there is functions for which that is not necessarily true. However, the set of the points for which the function is not continuous must be countable, otherwise it would not be true. However, it can be infinitely many points, all right? So, but almost every mirror means exactly that. Maybe you remember that, so I want you to basically look it up again. That is one of the conditions, basically. So this is a sufficient condition for the Riemann integral to exist. If this is true, then a function is Riemann integrable. And it is Riemann integrable if this is true. So that is not just a sufficiency, but also a necessity for a function to be Riemann integrable. Anyways, I'm going to continue now. So we're going to look at the so-called Riemann-Stieltjes integral, which is different. For the Riemann-Stieltjes integral, I mean, at the first sight, it kind of looks the same. But what you do is, actually, you put the integrator, which was s, into a function. So you're not integrating with respect to s. You're integrating with respect to a function g of x, okay? And that is going to be a function on that interval, okay? So let me explain. So I'm going to basically introduce a function g, for which basically that must be actually, its domain must be that interval, of course, okay? And that has something to do with the Stieltjes component of the integral, okay? Everything else will be the same. And what I'm going to do now is I'm going to put the increments of the integrator into that function. So you're not integrating with respect to s. You're integrating a function with respect to basically the increments of that. So this is basically what it will be. Okay, so that is just, some function. What kind of properties does it have? It's just out of question right now. And then this is going to be the limit, okay, for which I represent it like this. So keep in mind the integrator is the function g now, and that varies basically with respect to its argument. Okay, so not basically s, which was the case for the Riemann part. It is g now, and which means that for those differences, you calculate basically here, the endpoints at that function. The most common one is the logarithm, by the way, in finance especially, when you basically look at the increments. I would go to like this, so you can say simply just the logarithm of let's say some process, what is going to be a stochastic process anyway, but it can be deterministic. So if you have basically a deterministic one, that should be it, okay, because the differences in the logarithm would correspond to returns, okay, and that is basically the most common one. Anyways, if that limit exists, so you put basically those endpoints of the subinterval into the function and see whether basically this thing converges or not. Okay, this means actually rescaling the x-axis, right? So if you put basically the logarithms into that you're rescaling the x-axis, technically speaking, and you recalculate the area of the function for a rescaled x-axis. Of course, you're also rescaling the endpoints there, but that's just basically the issue. Anyways, okay, so if this limit exists, and you can call it the increments of g, which would be, if g is equal to the natural logarithm, that would be basically the returns. Okay, so finance is basically a major application for that. Then that would be called the Riemann-Stieltjes integral. Okay, so that's basically the other version. Of course, the Riemann integral is a specific case for the Riemann-Stieltjes integral if actually the function g is equal to the identity. So it is equal to, let's say, I'm calling basically the arguments s now. If it's equal to the identity, then of course you can see that the Riemann-Stieltjes integral is a general case of the Riemann integral, whereas the Riemann integral would be a specific case of the Riemann-Stieltjes integral if the function g is equal to the identity. Now, you can apply integration by parts, how to get there, because the question would be how to get this integral. I'm going to give you two statements basically for that, but that will not be the major focus because we're going to talk about stochastic processes. But sometimes you need to basically understand how to crack it. So simply if you have something like this. Now, it cannot always be done. It's just basically, it depends on certain circumstance, especially the properties of the function, which is now the integrator. And the question is how to get it. Now, integrating by parts, again, given certain circumstance, yields the following. So you have the function f at point b, which is the upper end point of the interval on which your function is integrated, times the function g at point b, which is also the upper end point, and then minus the functions, or the product of the functions at the lower end points, and then, of course, minus the integral from a to b of g of s, you can see, and then you have basically df here. Okay, so then, of course, f becomes the integrator. So you can swap basically the two if this is easier. Okay, it can be done if basically, for example, if fs is equal to the identity, for example, and then you could just change that, and then the function g would be equal to the logarithm. Then you would be doing it like this. Okay, so you can swap basically that. It can be done, and that is coming from integration by parts. Partielle Integration, that's a German term. Okay, of course it has to satisfy certain conditions. So then, of course, it can be done if both functions are actually Riemann integrable in that sense. Anyways, okay, so that's basically one condition number one, and condition number two, or how to get it. This is more common. If the function g is differentiable almost everywhere, which means that its derivative exists, because sometimes it doesn't even exist, but if it does, at least for which is not true, it could be basically points that are continuous, you can calculate this integral by calculating the following integral from a to b, namely f of s times g prime of s. So you have to have that derivative, otherwise it would not be basically working. And that is done when you calculate, for example, the expectation of a random variable. So this integral is actually the expectation of the random variable if g prime is the density of the random variable, and f would be basically just the identity then. So that is actually, I mean, if g prime is the density function, then that would be actually equal to, and you will see this later on, the expectation of f of, let's say, a random variable, which I call him, you can call it x if you like, it doesn't really matter. So I'm going to use those colors, and you can see this over here. All right, that's it. Okay, guys, let me check whether it is working. So it's supposed to, but I'm not always sure, but it does. Anyways, okay. We are going to continue. Anyways, all right. So those are basically the two ways, there's two standard ways how to crack the Riemann-Stieltjes integral. Whether basically you prefer the former or the latter depends on properties of the function as basically functions f and g, which I'm not going to discuss here because I want to talk about basically the stochastic context. But I'm going to introduce actually some two major applications for those, and that is going to be so-called total variation of the function, and then the so-called quadratic variation of the function. I'm going to start with the total variation of the function. The total variation of the function will simply be just the total change of the function. And I'm going to talk about that soon, so you can see this basically, how it will be. So what I'm going to do, and this is what the notation that I introduce here. So I haven't seen this, to be honest, very often. In fact, I haven't seen this at all. So that kind of resembles basically, I mean, how would you think about it? Basically, you're having the absolute value outside of the integrator, and the answer is simple, because I'm going to look at the limit here. So if I'm basically addressing this limit, which is actually addressing the total variation of the function g, because you will see that these are the increments of the function g, and then you take the absolute value of the increments, which means that you calculate the change of the function within that interval from starting at point si minus 1 and then si, so that will basically depending on that partition. And then what you are doing is basically taking the absolute value of that, and then you increase the number of sub-intervals, which I haven't said before, which is the case. So you stay basically in the same frame, and then you would analyze basically what happens to the total change of the function. And if this is finite, then we call it basically the total variation. Again, to be honest, guys, I haven't seen this notation so far, if I recall it correctly. I need to be honest. But this is, I think, a very practical illustration or very practical notation for it, so I don't need to use basically anything else to express it. And why not basically using the integrals as a notation? Because that is also some sort of limit of a sum. The only thing that you'll have here is that, of course, regarding the increments here, you have the absolute value outside of it. But why not, actually? So I thought, okay, I might introduce you to that. So this is said to be actually the total variation of the function. It's called total variation because it reflects the total change of the function between basically those 2 points A and B, okay, as the limit basically, or as the mesh of the partition is increased. As you can see this over here, we're looking at the limit of that. So when you have infinitely many sub-intervals between A and B, what happens to the total length of the function? Now, for example, if it's a linear function, it doesn't change, right? So it doesn't depend on the limit, but it can be some sort of weird function anyway. Okay, so this is said to be the total variation of the function of the function A to B. So the total change of the function. So even if first the function goes up and then it goes down back again, the total variation of the function will not be negative as soon as it basically it would not be zero as soon as basically the function changes at least once. Anyway, that's basically what I'm going to introduce you to. And the second one is going to be the quadratic variation, which is the quadratic change, okay, that will relate to the variance of some stochastic processes or increments and so forth. So this is where basically what I'm going to, okay? So we have the absolute variation, or sometimes you say the total variation, whereas you have a quadratic variation, which is you can call it the quadratic change. Okay, so you square the changes basically of the function, and you take the limit of that basically you're staying within the interval from A to B, and that's going to be the quadratic variation of the function on that interval. Do you understand these terms now, guys? Okay, I hope basically you do. There is a relation between quadratic variation and, of course, the total variation, which I'm going to discuss. And the relation is going to be the same, or it's not the same, but it's going to be similar within the concept of stochastic processes. Okay, so that is basically what the major task is going to look like. So you see this later on. And I'm going to basically talk about that. Okay, now first relation is that if the total variation is finite, so if the absolute change of the function is finite, which is actually true for most functions, by the way, that you're familiar with. If the total variation of the function is finite, then the quadratic variation is going to be 0. Okay? Now keep in mind there's going to be some sort of limit. I'm going to prove that, and that is going to be also transferred for stochastic processes. So that will be the same, although the limits here regarding the total variation and the quadratic variation are going to be expressed a little bit differently than I do here. Because these functions, keep in mind, so I'm going to talk about the function g especially, is a deterministic one. It's not a stochastic, basically, process. It is a deterministic function. Now, let me write it down again. So if g is, of course, continuous basically on that interval, that continuity one would be one point, and the total variation is finite. So if it's continuous and basically it has a finite total variation, then this implies that the quadratic variation is going to be 0. That's statement number 1. So the quadratic variation is going to be 0 if the function is, number 1, continuous, and its finite variation is, its total variation is finite. Okay? So then basically the limit of the sum from the quadratic changes of the function is going to degenerate. Okay, that's a very important statement, guys. Now, if you reverse it, which means that this is going to be just a logical contradiction or logical conversion, by the way. So I'm going to converse it. So just what I'm saying is this. So if, let's say, statement X implies statement Y, then you also have that the negation of Y implies the negation of X. So what I was saying is this. if the function is continuous and has a finite total variation, referring to basically to the statement x, then the quadratic variation of the function is going to be 0. You understand the point? So if the quadratic variation of a function is not 0, which means that you have the negation of y, then of course the total variation will not going to be finite. That's the conversion. All right? So that's basically what I'm also adding to that statement. So it's enough to prove that. Okay? It is enough to prove this statement, because if this statement is true, then the other is also automatically true. So you don't need to prove twice. You just simply prove it once. Okay? All right? Let me say it again. So if a function has a finite total variation, then its quadratic variation is going to be 0. So which implies, on the other hand, that if the quadratic variation of a function is not 0, then the total variation of the function will not be finite. Do you understand the point? Okay, so that's basically just actually the logical counterposition to the previous statement, which again, I'm just simply adding here to the context. So that's going to be statement number 2. Okay, it's enough to prove basically the first. Okay, now if the quadratic variation of a function is finite, okay, which means that, and now saying, okay, if it's 0, then it's also basically finite, but not 0. So if I say finite quadratic variation, which means not 0, if it's not 0, then the total variation will not be finite. Okay, so that's basically, you'll have it. Okay, so the total change of the function will not be finite. Keep in mind, guys, this is a very important statement which will be true for the Wiener process, because when we talked about it 2 weeks ago, the Wiener process is a specific stochastic process. I'm going to recall it. And keep in mind, it will have a finite quadratic variation. So that means that the total variation, the total change of the process will not be finite. Okay, so this is basically what I was proving that statement already here. So formally, if the function is continuous and if the quadratic variation is finite but not 0, okay, so I'm going to write it down here. So again, because 0 is also finite, right? But that was basically the logical counterposition. So again, what I'm saying is this: if the total variation is finite, then the quadratic variation would be 0. If the quadratic variation is not 0, then the total variation will not be finite. So that will diverge. Okay, and that's basically just the logical counterposition. So, and that's, okay, I was basically declaring that statement. But you will see later on today that the so-called Wiener process will have a finite quadratic variation, which is not 0, by the way. So since the quadratic variation of the Wiener process will not be finite, its total variation will diverge. Okay, and that is basically what one of the very important statements that I'm going to make today. Okay, now we need to prove it. So it's so important that I would basically prove that statement. Okay, but again, I was just proving one way. Okay, so there is 2 statements around it. Let me just basically recall those 2 so you understand the point. Statement number 1 means the following: if the absolute variation or total variation of a function is finite, then its quadratic variation will be 0. So this means that if this is not true, which means that if the quadratic variation is not 0, then basically the total variation will diverge. Okay? And again, just to remind you guys, it is enough to prove this statement, because if you prove this statement, you automatically prove the other. You understand the point? Again, the only thing that I will need for this is continuity of the function, but I introduced you to that concept. You know what it is. Continuity means that the image of the limit will be equal to the limit of the images, or the limit of the images will be equal to the image of the limit at every point of the function in every sequence on that interval. Now, okay, I'm going to look at that. So we are basically just formalizing here. So this is basically the quadratic variation, or not, this is not the quadratic variation, because the quadratic variation would be the limit of this thing, okay? But that is basically what you have for the sequence. And we're going to look at this sequence now. And if this sequence, okay, well, going to look at later on. So we're going to see that further. What you can do, okay, so we're looking at those members. Again, these are members of the sequence, and the limit of the sequence will be the quadratic variation, if that is basically a limit, by the way. Now, looking at the members of the sequence from the quadratic variation, you find that none of the members can be greater, and that's basically the point here. So it cannot be greater than the following expression which you're about to see on the right-hand side. What you're doing here is going to be the following. So you split that part into two parts. Okay, so whatever basically this is, I'm going to look at that member. Okay, so inside this, again, the series is actually what is supposed to converge, not the sequence. But again, I'm going to basically address the sequence from those series also. Okay, so when you have, for example, this, that let's say you got a minus b squared, again, whatever a and b is, because that's going to vary, cannot be greater than the maximum of basically of b minus a, if there is multiple ones. Okay, so whatever that is, so you select them basically the maximum, and then multiplying basically times b minus a, or basically we have the total variation, and you will go with the sum. So your sum of those actually cannot be greater than basically here. Okay, so that's basically the statement you're about to see, but it takes time to write it down, so I was just basically introducing to it. So whatever you do, okay, you take the maximum of the squared distance. Okay, so again, g at point si minus g at point si minus 1 to the second will be the squared length of the basically of the function on that partition, right? Okay, now you take the maximum out of those actually squared, variations, you can say, because this is basically what you have, and then you multiply it by the rest. So whatever this is, it cannot be greater than that. Okay, and this is something that you should see finally after all. Okay, so you take basically the greatest distance out and split the square into two parts. As you know, a minus b squared, right, is equal to a minus b times a minus b. This is not difficult to see. But you take out the biggest one, which is here, right, because there is multiples that you sum up. All right, so you have the sum of those squared deviations, let's say, and you take out the greatest deviation, and then you multiply that by the sum. It will not be greater than that. You understand that statement? All right, so after all, it's not that very hard. Now, here is actually the total variation, of course. All right, so you'll see that basically what will happen. And now I'm going to use the fact that the function is continuous. Since the function is continuous, this thing, the maximum, will converge to 0. This is what is going to be the case. Why is that? Because the function is continuous. Let me remind you what continuity means. Continuity means that actually the limit of the images would be equal to the image of the limit. Okay, so there is no jumps actually between the two. So that will be converging to 0 due to continuity of the function, as I assumed. So I'm not saying it has to be continuous, but if it is, that this thing will converge to 0. Okay? I'm going to write it down. So since the function is continuous, this means that actually, the greatest jump will converge on that interval, will converge to 0. Otherwise, the function would not be continuous. All right? So that is basically what it will be. So this thing will converge to 0. And this is the point now. If this is finite, and this is basically what you'll have next. So if this expression on the right-hand side, which is part of the total, it's not the total variation, the limit of that will be the total variation. But if this is finite, as actually the sequence progresses, right, which means that the total variation is finite, then this thing will converge to 0. And that's the proof. Simple as that, okay? So it's not actually that difficult to understand here. If this is 0, and this is finite, or this is not 0, let's say the limit of that is 0, and the limit of the other one is going to be finite, then the whole thing will converge actually to 0, because limits are as you might know, multiplicative. So the limit of a product will be the product of the limits, right? And there is no way basically for this function to escape, because this is always non-negative. I forgot to write it down. So the quadratic variation cannot be negative, of course. You understand the point? So the upper end point is going to converge to 0. The lower end point is already 0, and that's going to be squeezed in. So what happens is basically that the limit of that sum regarding the square distances of the function within that interval must converge to 0. There is no other way, basically, if the total variation is finite. So this is basically addressing the total variation, the finiteness of the total variation, and the function is continuous. So any function which is continuous and having a total variation that is finite will have a quadratic variation that is equal to 0. You understand the point? All right, so that is basically it, and that's the proof. And that also illustrates the other way around. So if the quadratic variation is not 0, but at least finite, I don't know what this is. This is basically probably some sort of sickness or so. If the quadratic variation is not 0, well, let's say finite, okay, then the total variation cannot be finite. You understand the point? If the function is continuous, by the way. So continuity basically prevents it. So if this is converging to 0, but that does not, then that can only be achieved if this will diverge. You understand the point now? So that's the same statement. I mean, it's not the same statement, but that is the equivalent one. You understand the point? All right? Okay, well, okay, that's actually it. So you see this over here, and we have proven that one. Okay, now there is another one which I'm going to show you, because the question is, okay, when is the total variation finite? So if, again, because if it's finite and the function is continuous, then its quadratic variation will converge, or will not converge, it will be 0, right? That is it, because the limit is the quadratic variation. You understand the point? So the question would be, when is the total variation finite? So when is this happening, for example? Now, there is multiple sufficiencies to examine that. There's just sufficiencies that I found, actually. But there is one which is, most of the time, can be achieved, it is achievable. When is the total variation finite? Because then the quadratic variation would be 0. For example, okay, so I'm going to write it down, basically. So here it is. Then the total variation is going to be finite if, and there is going to be the conditions that the function is supposed to satisfy. Number 1, okay, so condition number 1, or alternative number 1, if it is monotonic. Okay, at least, okay, so i.e., what does that mean? It is non-decreasing or it is decreasing. Or non-increasing, sorry. So it's non-decreasing or non-increasing. Okay, it doesn't have to be strictly increasing, and it doesn't have to be strictly decreasing. But, of course, if it is strictly increasing, then it's non-decreasing. Okay, so if you gain weight, you don't lose it. But you don't lose weight doesn't necessarily mean that you gain weight. You understand the point? Okay, so one does not necessarily imply the other. Okay, so if you gain weight, you don't lose weight. But if you don't lose weight, it doesn't necessarily mean that you gain weight, right? You can be stable. You understand the point? All right, so if the function is strictly increasing, then it's non-decreasing. And if the function is strictly decreasing, then it's going to be non-increasing. But just because it's non-increasing doesn't necessarily mean that it's going to be strictly decreasing, and the other way. So that's one condition. So it could be something like, I mean, it doesn't have to be the case, but if it is, then the total variation of the function would be finite. Okay, so I'm going to show you basically 1 or 2, so you understand the point now. Okay, so let's say you have here are the points A and B, and a function which could be a non-decreasing function could look like this. For example, like this. You see? Okay, so in the first half it is stable, let's say it will stay the same, and then after that it's going to strictly decrease. That's a non-decreasing function, and that will have a finite total variation. You understand the statement now? Okay, it's not a necessity, but a sufficiency for the function to have a finite total variation, which also implies that the quadratic variation of the function would be 0. So the quadratic variation of that will be 0. You understand the point? Okay. And second alternative, okay, which I'm going to introduce, of course, in this or, it can be both, okay, but which is not, it could be, it is common. So the second alternative is that is going to be continuously differentiable almost everywhere. Again, almost everywhere means for the points that which is not true, they need to be countable. So there is just countably many points for which is not true. And continuously differentiable means that it has a continuous derivative. That's the point. Okay? Differentiable means that it has a derivative, and continuously differentiable means that the derivative is continuous, at least almost everywhere. If that is true, then the function will have a finite variation. Okay, now I'm going to look at that statement also, because I want to prove that. So first, again, these are two different ones, and I'm going to first prove the first one and then going to prove the second one. So the first statement was that if the function is monotonic, which means that either non-decreasing or non-increasing at least, then it's going to have a finite total variation, which means that it will have a 0 quadratic variation also. So that's a major implication. Let me say this. So if, let's say, you have a stochastic process which is not stochastic, which is basically means that it goes up all the time, or it doesn't change. If it goes up or doesn't change, it will have a finite total variation, and it will have a finite total variation that basically, this means that it will have a 0 quadratic variation as well, but only in the mean squared sense. Anyway, so I'm going to look at the first statement. We are going to assume that the function is non-decreasing. Either it's non-decreasing or non-increasing, right? And I'm going to assume that without loss of generality, of course, because if I assume that the function is non-increasing, that works the same way. So it doesn't really matter whether basically you fix on the one or you focus on the other. You can basically just address both without loss of generality separately, okay? Because if it's not true, if it's basically non-increasing, then it works the same way. You're going to see this, so I'm going to make the correction after all. What does that mean? What does that mean that the function is non-increasing? So if a function is non-increasing, let's say x is less than y, then this means that actually what you have is that the function at point x is also not, let's say not greater, at least, than the function at point y. That's a non-decreasing function, okay? You understand the point? Okay, it doesn't have to be strictly increasing, but it has to be non-decreasing at all, okay? Now, keep in mind, guys, that this is a strictly increasing sequence. So the partition itself is going to be a strictly increasing sequence, which means that the function at the lower endpoint, which, as I'm going to write it down here, so the function at the lower endpoint will not be greater than the function at the upper endpoint of any subinterval there is, because otherwise the function would be not non-decreasing. You understand the point? If there would be the possibility the function to decrease, okay, for a upper endpoint of any subinterval, then the function would not be non-decreasing. So non-decreasing function means actually just that. This is an implication, by the way, okay? And that is true for every point of the partition at all, okay? So the next one will have actually an image which is never less than the previous one. You understand the point? Because otherwise the function would be not non-decreasing, okay? Now, if this is true, then what? Because that's basically the property. Then what? I'm going to look at basically the integral, because I was talking about it, okay? So you see basically what the total variation of the process would be. We're going to look at that one, okay? So we're going to split this one. And the first thing that I do is going to write it down, the definition. That's the definition of the total variation, guys. The limit of this sum. And the sum refers to the distances of the images, or the sum of the distances basically of the, how do you translate this? The total sum of the variations, you can call it, basically, within the subintervals, right? And, okay, now we're going to use the fact that the function is, we have that, okay, which is true. And then what? Okay, so then basically, I mean, what you can do is you can skip the absolute values, okay, because whatever is inside basically the absolute value, I'm going to write it down, so you don't need them anymore. And if the function is non-increasing, then you simply just multiply that by -1. That's not going to change either. Okay, so you would just simply multiply it by -1. Why can you skip it? Because if the function is non-decreasing, then the content here is never negative, no matter what. Okay, so actually the function, the function at the upper end point of the subinterval must be always greater or equal to the function at the lower end point, because otherwise it would not be the case. Okay, so you can skip basically the absolute values. Now, if you just simply eliminate the absolute values, which you can, there is simply just the increments of the function, right? So that is basically the upper end point. I mean, some people don't understand this, but let me just basically more specific. The first sum end would be here. Again, so if you, I'm gonna basically just analyze without the limit. Okay, so let me just basically just express it without the limit first. This is going to be the function, I mean, regarding the first sum end, at point S1, okay, and then minus the function at point S0. That would be the first sum end, right? Because that's going to be the first increment of the function, which I refer to. Then plus, because then comes the sum, right? So you have the sum here, so then comes plus. The second sum end will be the difference of the function at point S2 minus the function at point S1. So when you basically calculate those, okay, I'm not going to stop here because the sum doesn't end here, right? But when you basically calculate those, you'll find that the function at point S1 and the function at point S1 here eliminate themselves because you subtract those, right, from each other, you see? Okay, and that is also true if you continue summing up, right? So the only things that actually remain here is the function at the last point, which is the point B, by the way, so Sn, which is the point B, by definition, right? And then the function at point A, and that's it. And that is actually, well, that is, I mean, that is finite, right? Okay? If basically the function is finite at those points, you see? So that is basically what the total variation of the function will be. Now, if the function is non-increasing, so you change the word basically to non-increasing, that will be also still finite because the only thing that will change is the absolute value or inside. You can simply just bypass this when you just write it like this, and then you have just simply just its negative counterpart, okay? But it will be positive because, you know, the function would be actually, so if you multiply that, which is negative, okay, so then that would be basically negative, it would be simply just positive again. Okay, so the total variation is not negative, okay? But that's the only thing that would change. So you don't need to check that one. You understand the point, okay? So then the function, if the function is non-decreasing, then the function will have a finite total variation. And what will be the quadratic variation of that function? The quadratic variation of the function is going to be 0. That's it. So that was statement number 1. This is going to be finite. The total variation is finite. So this thing is finite at that point if the function is non-decreasing, on the interval at least. You understand the point, guys? Okay. All right. Now, let's go basically further. I'm going to show you the second statement now. What was that? If the function is continuously differentiable. Continuously differentiable means what? It has a continuous derivative. Okay? So, we assume that. Okay? So, we assume that basically the function is continuously differentiable on the interval. So, if this is true, then the so-called mean value theorem of calculus, or the mean value theorem of differentiation, how it's also referred to, I'm not sure if you understand that, basically addresses the existence of a point that satisfies the following equation. The function g prime, which is the derivative of the function, at that point, which is I refer to as SI asterisk, is, again, is equal to the ratio of the following two things, okay, which is, again, so this is actually, let me illustrate that. So I'm not sure if you understand this statement, but I'm going to basically illustrate it so you understand it better. So let's say I'm going to look at the partition between, here you have Si minus 1 and Si. And the function, let's say, goes like this. Okay? Let's say without loss of generality, you understand the point now. Now, what is basically, so this is the function g, okay? And this is the point g at point Si, and that is going to be at point, at point Si minus 1, and that is going to be at point Si. And what about this expression? This expression is going to be actually the slope of this line that connects the two. Okay, I'm going to try to do it again. You might see this better after all. It's not visible that much, so maybe like this. Now, the main value theorem of differentiation claims, again, so this is going to be the slope of this line, because the length of this, actually the vertical line, corresponds to the numerator, and the length of the horizontal line corresponds to the denominator of that expression. Now, the mean value theorem implies that there is some point between the two. Let's say over here, okay, which I refer to as S asterisk, between the two, somewhere, at which, okay, that has the same derivative, or which is equal to the slope of the yellow line. You understand it now, okay? So though the brown one, which is actually this part, and I'm talking about the slope, right? So I'm talking about the slope of the brown line, and the slope of the yellow line are equal. This is basically what it means, okay? I'm not sure if you understand the point, but the mean value theorem of differentiation implies the existence of that, okay? Now, so I'm going to basically make use of the fact here, and you need to understand that Si asterisk is some point between Si and Si minus 1. Now, okay, so I'm going to use the definition again, which is the definition of the absolute variation. I'm going to write it down again. Sometimes you say total variation also. And I'm going to change basically this, the numerator here, by the g prime at that point times Si minus 1, which is going to be here, of course. And then, since basically I'm looking at the absolute value, I would need to consider the absolute value of that change, right? So whether it's positive or not. It depends on it, okay? Keep in mind that this half, so I'm talking about the denominator, sorry. I'm talking about the denominator here, which is also here, is always going to be positive. That is because this sequence is strictly increasing, right? It is a partition. Here you see it. It's a strictly increasing sequence. You understand the point? Now, interestingly, and this is something you say, right? This is the Riemann integral of the function g prime, or let's say the absolute, or the Riemann integral of the absolute value of the function g prime. And when does that exist? And we were talking about it. The function is Riemann integrable. And the reason is because it is, and then simply, it is continuous almost everywhere. So if the function is almost everywhere continuous, then it is going to be Riemann integral. And why is it always basically continuous almost everywhere? Because it's continuously differentiable almost everywhere. I'm supposed to have said here that is almost everywhere, right? Is continuously differentiable. So I wasn't precise in that regard, but which is a weaker concept, by the way. So it doesn't even need to be continuously differentiable, right? But it needs to be basically almost, if it is continuously differentiable almost everywhere, then it's going to be Riemann integrable. That's the point. So its derivative, or the absolute value of the derivative, is going to be Riemann integrable. So that is going to be finite, right? Because this is, and as you see, this expression, all right, this expression here, maybe I should have written that down, but this expression is equal to the Riemann integral of the absolute value of the function, okay? So g prime, of course. So g prime is the function that I'm integrating here with respect to s, okay? So that's calling basically the integrator s all the time. But that's going to be it, okay, from a to b, of course, right? And s is going to basically vary here inside the function g prime again. Let me write it down so you see it better. Here it is. This function is going to be Riemann integrable, right? Because if it's continuous almost everywhere, then it is Riemann integrable. You understand the statement, guys? Okay, so that is basically what I'm supposed to show you here, and this is basically what I had done. You understand? So I'm connecting those two. And later on in the second half of this lecture, I'm going to talk about that within the context of stochastic processes, which is not going to be more difficult than that. Okay, so if you understand that, you are going to be very well transitioning to stochastic processes. Okay, yeah, so, okay, I'm going to look at the variations. And I'm going to look at, first of all, the variation of the identity function. As I talked about it before, the identity function gives back the argument, right? So you have it basically coming back, and since actually the function is strictly increasing, which means that is non-decreasing. And if the function is non-decreasing, then what? Then the variation is, the total variation is going to be finite. That's the point, right? Okay, I was writing that down here. So the total variation of the function when it comes to the identity is going to be finite. Okay, I'm going to, okay, I mean, you can change it like this. And what it is going to be, I mean, okay, you can break it down a little bit. So if you want to, you can break it down, but that's a statement that I was making. How would you basically address a total variation? So I'm talking about that. It's not difficult to see what it will be. The total variation of the function, if it's the identity, is going to be equal to b minus a, by the way. That is for sure. But why? Now, again, what is a total variation? The total variation is going to be the limit of the sum, okay, of the absolute value of the total distances. Okay, so you have si minus 1, right? So the sum of the length of the subintervals, which is equal to basically the total length. So they will be equal to Sn minus S0, which is actually b minus a then. You see? And that is finite, of course. Okay? What it would be. So that is going to be basically true here for those. Anyway, so thus, again, you don't need to have actually the absolute values here anymore, because the partition is a sequence which is strictly increasing. So you don't need to look at the absolute value of the increments. You see? So that's going to be it. If you can skip basically the absolute value here for the increments, even if the function is basically strictly increasing, you can do it. All right. Anyways, okay, so, and then of course the quadratic variation is going to be 0. We have proven that. So I was writing it down again. This is the quadratic variation. And the quadratic variation, of course, here you see it again, is that this is the definition. That would be the sum of the squared distances, or the limit of the sum of the squared distances of the endpoints here from the partition. And which is going to be convergent to 0, right? The sum. I mean, of course, you have the limit of the sum of the squared distances of the, actually, of those endpoints. But there is no other way to express it, okay? So you take basically the differences between the upper and the lower endpoints from the partition, you square them, you sum them up, and you take the limit of them as basically the number of subintervals increases. And you'll find that that's going to converge to 0. We have proven that, so you don't need to. Okay, so if I ever come up with a question like this and you find that the total variation of the function, it would be finite, you don't need to show that the quadratic variation would be equal to 0. I mean, you can, but you can simply refer to it, okay? I've written that down in the readers, so you can take those readers into the exam, by the way. I talked about it. Now, when it comes to stochastic processes, I want to basically put that into right context. So I would need to change the limits, of course, because the processes are random, right? So when it comes to random variables, I would need to change them. And the way to do it is by simply replacing those limits by the mean square limits. Okay, so let me recall basically what the mean square convergence was. So let's say you have a sequence of random variables. And again, we've done this, so I was introducing to it. And what is a mean square convergence? And I will also look into the implications of that. The mean square convergence is, or we say that the sequence is set to converge in a mean square, right? That was a term. To, let's say, to another random variable, mostly it's another one, right? Which are called the limit. So the dark blue one is the limit, and the purple ones are the members of the sequence. If the following statement is true. If, and this is what I'm going to address here, the limit of an expectation, and that's what I'm going to address here. And what is going to be the expectation? The expectation is going to be taken from the squared distance. So the expected squared distance between the members and the limit is going to basically converge to 0. Okay, so the expected squared distance between the member and the limit is going to converge to 0. If this is true for a sequence and then for a limit, then this is basically what you'll have. Okay, now the notation was MS. You remember that. Convergence in mean square, or you simply say mean square convergence as the sequence progresses. You remember that one? Okay, there was infinity missing here on this slide, but I hope it doesn't bother you that much. Okay, we've done this before. This implies, among others, what? Convergence in probability. So that is a little bit stronger concept, but are not as strong as almost sure convergence. And we're going to replace, so when it comes to stochastic integrals, we're going to replace the limits that you just saw by their mean square analogs. Okay, so the mean square analog will be simply just replaced it with. I'm going to recall basically what the properties are. The properties are, if a random variable converges in mean square to another, then so does the expectation and the variance of that. And that makes it very practical in that sense. So the expectations will converge. Again, I'm going to recall that one. So again, so let's say this is true, then the expectation of the random variables will converge to, namely to the expectation of the limit. And the variances also. So the variances of the random variables will converge to the variance of the limit also. Of course, provided that the limit is, or those limits are finite, right? So let's say that the limit has a finite variance, because otherwise it doesn't make that sense. Okay, I'm going to show you that again. So why is that? Because the expectation of the squared distance, which you just saw, okay, I mean, I'm not sure if you recall that formula, but the variance of a random variable, let's call it y, equals the expectation of its square, sorry, I'm supposed to write it y, minus the square of its expectation. Okay, that is a very important formula I introduced you to just at the beginning. So the expectation of the square will be equal to the variance plus the square of the expectation. Because keep in mind, the expectation of the square, it's also true for the expectation of its absolute value. So this is equal to, basically, to the expectation of the square, but not only, this is going to be also the expectation of the absolute value of the square. That is also going to be true, because if you multiply it by itself, you don't need to basically take its absolute value. So that's going to be it, okay? So the expectation of the square distance of the members to the limit is going to be equal to the variance, okay, of the distance, right? Plus the square of the expectation of the distance, right? actually by definition for the variance. You understand that statement, guys? Okay, now if this is converging to 0, so the left-hand side is converging to 0, okay, and the others are finite, then they both need to converge to 0 as well. There is no way to basically to bypass that one, okay? Again, and the reason is because the variance is non-negative, okay? So it's not negative. So since it's not negative, right, and the square is not negative either, all right, so it doesn't, again, it's never going to be negative. It must converge to 0, both of them. Otherwise, basically, it will not be true. Okay, so again, so the variance converges to 0, and the square of the expectation does the same. Okay, and if the expectation of the square converges to 0, then of course the expectations of the members to the will converge to the expectation of the limit. That is actually the proof of the statement. Again, we did this last time, just by basically I wanted to give you the implication. So the most important implication regarding the mean square convergence, and that is the reason, is it implies a lot of things without putting too much restrictions on regarding the convergence, because almost sure convergence appears to be a very strong one, okay, which again is not necessarily the case, but it's also implying convergence and probability. You might remember that one, okay? Anyways, okay, so we're going to look at now the stochastic counterparts of the expressions that I just used. And one way to look at that is replacing actually the function f by a stochastic process. This is what we're going to do. Okay, so here comes the interval first, and you're going to see this. So again, the same partition and all that stuff, so that doesn't change, right? Okay, so just need to basically represent this the same way. Okay, same partition, you split basically the interval from a to b into multiple parts, and then maybe into multiple subintervals. Keep in mind, and never forget it, this is actually a strictly increasing sequence. Okay, so the upper endpoint is actually always greater than the lower endpoint of any subinterval of the partition of a and b. Okay, now when you try to replace basically by stochastic processes, I'm going to just define one. So x is going to be a stochastic process, and that was the reason why I used s instead of x to be the integrator, so you're not going to get confused. All you would need to do is just, when you look at the Riemann sum, because that was a Riemann sum that we talked about, you look at the Riemann sum of the stochastic process, and that's basically it. Okay, so you have the stochastic process at point si asterisk, which is basically some point within the ith partition of the interval a and b. Okay, so again, keep in mind si asterisk is going to be somewhere between si minus 1 and si. You can choose whatever it's basically supposed to be. But keep in mind, guys, that regarding call it the increments of time, because this is actually a time index, right? So the x-axis is representing a time when it comes to basically a stochastic process. So I'm going to call it the increments of time, if you agree to it. So multiplied by the increments of time, if this is, and that's important, guys. Okay, I was basically putting down a bunch of definitions here. So I was defining si asterisk, which is some point between the two. It can be equal to basically to the lower endpoint. It can be equal to the upper endpoint, depending on the sum. It doesn't really matter. But it can be also somewhere between. Okay? Now, if this converges, and check this out, in mean square, so that is the mean square convergence now. And we talked about it, what it is. If this means that the expectation of the square, right, of the distance between the two, is going to be converging to 0. And the limit is going to be called the stochastic Riemann integral. And the limit is, again, expressed by, actually, I was introducing to it when I was talking about the Brownian motions, right? But now, this time, I'm going to define it what it is, and that's basically the mean square convergence, the mean square limit of that sequence, actually. So this integral, and this is expressed like this, right, you see, is going to be called actually the stochastic Riemann integral. So you replace basically the function f that you just saw at the beginning of this lecture by a stochastic process, and everything else will be the same. And then, of course, accept the limit, of course, because you replace the limit by the mean square limit. All right? So that's going to be the mean square limit of that. And yeah, and that's basically all you would need to do. Okay? So this is set to be basically the stochastic Riemann integral of the process, okay, on that interval. So I forgot to basically to mention this here, but on this interval from A to B, right, is it? Okay, because if you change basically the interval, it could be also changing the integral as well. Okay, but that's, I think the notation should be clear. It kind of resembles to it. So you can interpret that to be actually, I mean, it's not the area that the paths are generating, because keep in mind the paths are not stochastic anymore, right? So but you could basically interpret that to be the case. So you could call it the random path. So this integral is actually, so when you have, let's say, the time points between A and B, so S denotes the time. I should have written down T, but sometimes I use T. Okay, so it doesn't really matter. So you could call it the integral to be actually the random area that the process generates. Okay? Or the limit of the random area that the process generates, because I always, split that into multiple parts. You understand the point? Okay? So you could interpret that in this way. It's not precise, but again, because the paths, as soon as you see them, are not stochastic anymore. So this is actually the Riemann integral, right, of the orange function, because the orange function is, I mean, assuming that is going to be Riemann integrable, right? You understand the point now? Okay, but this is a random variable, so keep it always in mind. So these integrals are going to be random variables now, okay? And those random variables are going to be, so this is a random variable, right? Or a stochastic process, to be precise. But a stochastic process can be also interpreted to be a random variable depending on time. You understand the point? Okay, does that make sense to you? Okay, well, and yeah, so it's not a big deal. So transitioning to the stochastic versions of the Riemann integral is not a big deal. However, regarding the Riemann-Stieltjes version, that's going to be a big deal, because the function here x is not supposed to be stochastic anymore. It's going to be a deterministic one again. The increments are going to be stochastic now. And this is a little bit more difficult to interpret. So I'm going to change it to y. And of course, you can see that, so y is going to be a stochastic process. And now I'm going to express them basically regarding their increments. So this is the random increments now, right? Multiplied by a deterministic function. So keep in mind, guys, the stochastic Riemann integral, Riemann-Stieltjes integral is not that stochastic, because only the increments are stochastic. The function is deterministic now. It must be a deterministic function. If that is also stochastic, that is going to be a big deal, but not now. So we're going to look at that maybe after the break or so. But again, this is just one part. Okay, so regarding the Riemann-Stieltjes integral, basically, the increments are stochastic. The function that you're integrating now is going to be deterministic. Okay, and yeah, so basically the mean square limit is set to be the stochastic Riemann-Stieltjes integral. This is still stochastic because in that regard, let's say, I'm going to look at the function, the integral, there is still going to be a deterministic function now, but the increments are going to be stochastic now. So the function is deterministic. You understand the point? Okay, so this is the transitioning only works when you look at stochastic increments now. Okay, random changes. Okay, so now the changes are random, right? Multiplied by a deterministic function. Okay, now this cannot be addressed by limits, okay, or let's say areas in the same way that I did basically for the previous process. Okay, well, you simply multiply basically the increments by a deterministic function, And that is going to be the mean square limit of that. So you can see this over here, right? Okay, so the changes are random now. Okay, you have random changes. This is the increments. Check it out, guys. So this is the increments of the process at time point Si. And you multiply those increments by the random increments, by the way, by a deterministic function. You take the mean square limit of that. And the mean square limit of that is going to be the Riemann-Stieltjes integral of that. Okay, which is denoted here. That is a random process also. Anyways, yeah, so that's it. Okay, we're going to look at some examples right now. So we're going to look at the increments of a stochastic process first, where actually, so if you focus on that, you set basically the function that you're integrating. I mean, okay, in addition to it, I'm going to look at the starting value, which is supposedly be almost surely 0. And then I'm going to look at basically the, I mean, you can simply call it here, the function 1, let's say. It's not a function anymore, but you just simply have the increments of the stochastic process. Now, this is just simply the process at time point t minus the process at time point 0, which is, since it is assumed to be actually almost surely 0, this is simply just a process at time point t after all. Okay, keep in mind in this case, in this example, I'm integrating the function from 0 to t. So I'm integrating 1, basically, and looking at basically the Riemann-Stieltjes integral. That is true for every stochastic process you see, including the Brownian motion, by the way. Okay, so when you look at the increments of that. This is just a little example, okay? So you need to understand, and this is what I'm going to do now. These are the increments here, okay? And this is the mean square limit of that. You see? So that is a random variable here right now. So let me go back a little bit so you need to understand this. This thing, okay, will converge in mean square, right? So when you sum up those increments, it will converge in mean square to the process at time point t, because that is going to be the limit of that. You see? Now, okay, but you don't need to go that far because it's not going to be that technical, of course. When you look at those increments and you sum them up, of course, you get the process itself, right? So that is even not that is even also true without looking at the mean square limit, because that is equal to it, right? Of course, so, but that's still not wrong, but it's not necessary, actually. All right, anyways, but yeah, but that is still true. So you have it here. That's how you address it directly. Of course, the function or the stochastic process is going to be, at point 0 is going to be, let's say, by assumption 0 almost surely, right? So you can skip it, by the way. All right, that was one. Okay, now I'm going to look at another definition, because this time I'm going to look at the total variation now of a stochastic process. This time, not a function, of a stochastic process. And when you look at the total variation, so everything was going to be more or less similar. Please allow me to finish, and then we'll take a break then after all. So I'm going to give you that definition and that of the quadratic variation too. So when you look at that, the only thing that changes is the mean square limit. Okay, you can call it the total sum of the increments, by the way, and which is supposed to converge. And if it converges, then I'm going to write the limit like this. Again, so that was my idea to introduce that notation. I haven't seen it before, but why not? Why not using basically some sort of integral notation to express total and quadratic variations this way, okay? Now, this is going to be the case. So, yeah, and of course, if the limit exists, which means that it will be finite, okay? Almost surely, right away, because in this regard. Anyway, and so that mean square limit is set to basically to be the total variation of the process on that interval. And based on that, you can also define the quadratic variation too, which I'm going to. And then after that, we take a break. Okay, so if you allow me to finish that point, I'm going to look at the quadratic variation, which is going to be the sum of the squared increments, or the limit of the sum of the squared increments of the process. And yeah, and the mean square limit. So it's going to be the mean square limit of the sum of the squared increments of the process, which is the quadratic variation of that. Okay, and yeah, and you know basically what it means. So mean square limit means that the expectation of the square distance of this thing and this thing supposed to converge to 0, right? We're going to calculate the quadratic variation of a process, which takes time a little bit. So that's a little bit more difficult than to calculate a quadratic variation of a function, for example. But I'm going to show you that one later on, so that this is basically what the definition will be. So that will simply just, again, same definition. So transitioning to basically the stochastic counterparts is not going to be difficult. Same definition, but only with respect to their mean square limit. That was one of the reasons why I introduced you to those limiting concepts. And the mean square limit is, or was, one of them. So now you see, basically, you get the picture. Okay? All right, guys. Yeah, this is it. Okay? Yeah. Now, okay, before we move on, and we're going to discuss some properties regarding the finiteness and so on, we take a break. Okay, so let's take a break now, and then after that, we're going to continue from here. Okay, 50 minutes. Yeah, quadratic variation, there you go. Okay, so, yes, okay, we're talking about basically regarding quadratic variation and the total variation and the quadratic variation. Both the total and the quadratic variation are expressed in form of the mean square limit when it comes to stochastic processes. Now, the same principles are true regarding quadratic variations and the total variations. If total variations, or the total variation of a process is finite in the sense of a mean square limit, right? Then the quadratic variation was actually going to be 0. Okay, so I'm going to basically summarize that statement where the finite total variation implies 0 quadratic variation. I will need to change, however, in the sense of deterministic functions that was based on continuous functions, right? In this case, if, let's say, the function, which is the stochastic process, has continuous path, at least, basically, on the interval almost surely. So the paths are going to be almost surely continuous in this case, not the function itself, but it's quite the same thing. And all of them. So basically, they need to be continuous regarding basically the outcomes for every single, actually for every single outcome of a random experiment, which is underlying here. Then this is, again, basically the case. So if it's finite, if the absolute or the total variation of a process is going to be finite, then its quadratic variation is going to be 0 in the mean square sense. So again, quadratic variations of stochastic processes are defined as limits in terms of the mean square sense. Okay, so the same statement is true actually in this case. And yeah, that is basically the issue here. We're going to prove that, and the logical counterposition is actually similar. If the quadratic variation is not 0, these are expectations, by the way, so if you kind of wonder why this is the case, these are regarding expectations. If the quadratic variation is not 0, but at least finite, then the total variation is going to be actually divergent. Okay, so you see that statement over here. Again, if it's finite but not 0, again, so this is what I would need to address here. Of course, if it was 0, then it would be also finite. But if it's not 0, then the total variation would be diverging. Okay, so there is no mean square limit here for that, in that sense. The proof is very similar to that when it comes to deterministic functions. We would need to replace the mean square limit. Okay, so we would, again, so I was basically addressing that issue since the quadratic variation is always non-negative, whatever basically comes out. We only need to show that basically that the quadratic variation is 0 if the total variation is finite, right? Which, again, we discussed this because that the other statement is just simply its logical counterposition, and we would not need to consider the logical counterposition. We do it anyway. Okay, now regarding the mean square limit, there is not much change here. Only almost continue. I mean, the paths are supposed to be actually almost surely continuous. Okay, now we're going to look at actually the sum from which the limit is consisting of. So the mean square limit of this sum is supposed to be actually the quadratic variation, and we say that this thing, however, whatever it is, cannot be greater as the maximum, let's call it jump, okay, so we can say this here, within the partition of the process times the total variation, or the sum of the total length of the process, okay? Well, basically because the limit of that is supposed to be the total variation of it. Now, this thing is going to be actually 0 almost surely. Why? Because the function is actually continuous almost everywhere, right? So, and that is basically the issue, right? So since actually the stochastic process on that interval is continuous almost surely, or almost everywhere, right? Which means that basically you'll have this part where this is converging with probability 1 to 0. That's the issue, okay? So the probability that the jumps actually do not converge to 0 is actually going to be equal to 0 as well. All right, so this happens with probability 1. And yeah, and that is basically the case. So regarding the paths. And so since this is supposed to be the case, almost sure convergence is usually a stronger concept in that regard, okay? But there is no direct relation between convergence and mean and almost sure convergence. We find that since this is going to be actually finite, at least in the mean square sense, so I was not precise in that regard, but it's supposed to be finite in the mean square sense, and that converges with probability 1, you'll find that the total the quadratic variation is going to converge to 0 in the mean square sense, and that is basically a similar. Okay. Now, so the proof is quite weak in this case because I did not create the link between almost sure convergence and convergence in the mean square, but I would not need to. So typically, it's actually a stronger concept, by the way, although it has different implications. Anyway, so this is happening basically with probability 1, by the way, and so thus it will basically imply the mean square convergence as well. Now, regarding Brownian motions, which I'm going to discuss because I want to address the quadratic variation and the total variation of Brownian motions. The total variation will not be finite, and the quadratic variation, because the quadratic variation will be finite but not 0. Let me recall what a Brownian motion was. That was basically the topic 2 weeks ago. A stochastic process is called a Brownian. I mean, we were talking about the limit of the diffusion, reschedule, and the walk to be the Brownian motion. So that was more or less an abstract process in that regard because we were talking about the limit of that, but we were actually, I mean, the limit of basically in the distribution, but it doesn't basically matter. So a stochastic process is said to be a Brownian motion, okay, if it satisfies the following things. Number one, the starting value is going to be 0 at least almost surely, so with probability 1, which is not difficult to satisfy. Number two, or even to justify, the process at time point t has independent increments, okay? So the increments are independent. I will come back to that later on, which is going to be important regarding variations of the process. So we'll look at the increments, by the way, also. I mean, stochastically, of course, right? So when it comes to distribution functions anyway. Okay, the process has continuous paths, at least almost surely, so with probability 1. And again, we were discussing that also. And basically, it is going to be normal, right? So whereas the variance is going to be proportionate with respect to time. So I would like you to maybe to ask you to review basically last lecture where I was basically coming to that. Now I'm going to look at that again. If sigma squared is equal to 1, then the process is called the Wiener process. So that is a specific type, right? A specific case for the Brownian motion. And sigma squared was, I'm not sure if you remember it, when I was looking at the random walk, especially, that was the variance of the increments of the random walk, from which I was, looked at the diffusion rescat version of it. And yeah, so that was basically the process. Okay, so maybe you can kind of review basically how that can be generated, or I was generating it from a diffusion rescat random walk. Now, if you standardize it, of course, then you will get it back, right? So the Wiener process would be actually just, the standardized version of a Brownian motion, by the way. Now, so I'm going to focus on that one because I will basically just ignore the variance of the increments of the random walk. If the variance of the increments of the random walk is equal to 1, which was the case for the process that I was simulating, then of course you'll have a diffusion rescat random walk which is converging to a Wiener process. Now, I'm going to look at the quadratic variation as well as the total variation of the Wiener process, which I'm going to address. So that's going to be the major issue, and that takes a little time. So I mean, it's not difficult to prove, but it will basically, the structure of the proof is going to be a little bit more difficult to understand maybe. So I will need to basically to break that down a little bit. So the statement that I'm going to make is that the quadratic variation of the Wiener process is going to be equal to the time that it will basically takes on the interval. So let's say we have a partition without loss of generality of the interval between 0 and t. So that's basically the interval that I'm going to split, okay? And in that sense, I'm going to show you that, and that's going to be, let's say, the next big statement here, that the quadratic variation of the Wiener process is equal to t. That's a statement that I'm going to make, okay? But I need to be a little bit more technical, okay? So you have basically those points splitting the interval from 0 to t. And it's not necessarily equidistant, by the way, so that should be also denoted. And there is the Wiener process, and I'm going to basically create the mean square limit. No, not the mean square limit. I mean the mean square limit basically with respect to the quadratic variation first. So I'm going to show you that the quadratic variation, which again is going to be the limit of this expression. This is not the quadratic variation, this is the limit of that, the mean square limit, in the mean square sense, is going to be equal to t. So whatever this is, again, so this is just a representation, by the way. Whether it exists or not, this is a different story, but this is still how you could basically represent it. And what I'm going to show you that this thing is equal to t. That's it. That's going to be the first statement, the big statement here, actually, in this part. I created an exercise, and I would like you basically to review it. Okay, so there is an exercise coming up to this part where you would need to calculate this integral, let's say. You can call it like that, but this is just a symbolic notation, basically for the quadratic variation of the Wiener process. So that is going to be a big statement, and that is going to affect across the board every single statement I'm going to make afterwards about the Wiener process, including the Itô integral and including, for example, Itô's lemma. I'm not sure if you heard about that. Okay, but that will be basically playing a major role for the upcoming lectures as well. Okay, now this thing is equal to t, and t is, of course, finite. So since the quadratic variation is finite in the mean square sense, we'll find, and again, so this is not even random anymore, you can see, right? We'll find that the total variation based on that is going to be is going to be divergent. Okay, so if the quadratic variation is finite, then the total variation is going to be divergent. Okay, and yeah, so this is basically the limit of this thing is going to be the total variation, and here you see it. Okay, so again, whether this exists or not depends on certain circumstances, but if the quadratic variation is finite, then this is going to, I mean, you can write it like this, but if I say the limit is equal to infinity, that's not a limit, actually, so that contradicts itself a little bit, but regarding the formal representation, it should be fine. So it's not that big of a deal. Okay. However, I'm not going to basically talk about that one because that has been proven, at least intuitively. So I'm going to focus on this statement here, that the quadratic variation of the Wiener process is not just finite, but it's going to be equal to t. So it's not zero, by the way. Okay. All right. Yeah, this is what it's going to be. So here we're going to prove it. Now, this is a little bit more time-consuming in that sense. So I will try to break it down, at least the structure of that, try to break it down a little bit into multiple parts. Again, let me show you what we basically were about to see. When it comes to mean square limits, you need to understand that the expectation of the squared distance, so I'm talking about the square distance, so usually I would put that into the absolute value sign, but it's not that big of a deal. From the first part, which is the sum of the squared increments of the Wiener process. So here you see, here you're about to see the sum of the squared increments of the Wiener process. So inside the square, you see the increments of the process at point Si, and then at point Si minus 1, if you take basically the difference, basically that, this is going to be the square of the difference. So the sum of the squared increments of that, okay, this is basically on one hand. And the square of it, or the expected square of that, minus the limit, okay, which is supposedly be t. So that is the statement that I was making. Supposedly be t. This is the expected squared distance of this expression to its limit is supposed to converge to 0, because that is the definition of the mean square convergence, okay? So if the mean squared limit of this expression is equal to t, then the expected squared distance is supposed to converge to 0. This is the definition of the mean square convergence. Remember that, guys. Okay? Now, how to do it is going to be basically done by the following way. I told you that the expectation of the square is equal to the variance plus the square of the expectation. So I'm going to basically use that again. So the variance, since the variance of a you can call it a random variable, is the expectation of the square minus the square of the expectation. Thus, the expectation of the square is equal to the variance plus the square of the expectation, as you see, right? I'm going to break that down, so because you'll see that the expectation of the squared distance, okay, of this, let's say, random variable, which is the sum of the squared deviations of the Wiener process and its limit t, is supposed to be equal to the variance of that expression. Okay, so I'm simply just copying it right now. It's not a big deal. The variance does not depend on additive constants. So I'm not even supposed to write down minus t, but you can. Okay, so the variance will not depend on it, of course. So you can skip it, but I'm keeping it anyway right now. And then plus the square of the expectation. So the square of the expectation of the same expression inside. This is the distance of the random variable to the limit, the mean square limit, right? Or the deviation of the random variable to the limit, and looking at basically on this one. Okay, so that's basically what you're about to see, how I'm going to deal with that stuff. Now, let me tell you something. So I'm going to show you that the mean square limit here of that is going to be 0 by showing you the following statements. Number one, I'm going to show you that this thing have the expectation 0. So the square is going to be 0 too. And this thing, however, will converge to 0. So thus, the expression above will converge to 0 as well, which means that the random variable, which I talked about, that was the sum of the squared increments of the Wiener process, will converge in mean square to t. So that's basically the proof. Okay, so that's going to be the structure. Okay, now that takes time a little bit because you will need to address, and this is basically why it's going to be difficult. It's not difficult, but let's say it's not that straightforward, let's say, because I would need to address the variance of the square at some point. Okay, so the variance of the square is not very straightforward because that requires the fourth moment of the random variable. So I will need to address what the fourth moment of the increments of the Wiener process is. But I'm going to talk about that because I'm going to use the normality of the Wiener process as basically a tool. Okay? Now, first off, again, I'm going to basically address the expectation of this thing. Okay? So we're going to talk about that first because that's easier to see or to deal with. Okay? So the expectation of the squared increments of the Wiener process, because the expectation of the squared increments will be required for the expectation of the sum of the squared increments. And the expectation of the sum, since it has independent increments, guys, is going to be the sum of the expectations, and thus the variance of that is also going to be basically due to the independency of the increments. Okay? But I'm going to talk about the expectation of the squared increments first. The expectation of the squared increments is going to be, again, I'm going to use the same approach. The expectation of the square is going to be the variance plus the square of the expectation. So I will need to address the variance of the increments of the Wiener process and the expectation of the increments of the Wiener process. What is the variance of the Wiener of the increments? Now, since the Brownian motion, okay, I will talk about that. The variance of the increments, we will talk about it, right, is actually by definition the difference in the time points, right? Because due to normality and so on, and that is basically what you end up with, and the expectation of the increments is going to be 0, right? So this is, and keep that in mind when you're going to basically looking at it, the expectation of the squares of the increments of the Wiener process. Simple as, okay, which is equal to its variance, by the way. But I'm going to come back to it later on, because what I need is not just the expectation of the squares. I'm going to need the expectation of the sum of the squares. And the expectation of the sum is always, no matter what, the sum of the expectations. So you can simply just bypass the sum operator by the expectation operator. Or it's not, sum is not an operator, but okay, you can call it the operator if you like. So you can simply just change that. And then of course, you have the expectation of a linear transformation, which is simply the linear transformation of the expectations. So the expectation of that sum is the sum of the expectations, as you see. And then, of course, you have the sum of the expectation of the squares of the Wiener process. And that was the reason why I was basically splitting that apart, because this thing, as I found in the previous part, is simply just the difference between the upper and the lower endpoint of the partition, or the ith subinterval from the partition. And then, of course, you have minus t left, which is coming from here, right? Because the expectation of a linear transformation is a linear transformation of the expectations. You see that? And then, of course, what you do after all is what you have done before. You plug in your findings regarding the expectation of the squares, which was simply just a difference of the upper and the lower endpoint of the ith subinterval from the partition. And if you sum that up, of course, you're going to get t out. So you have t minus 0, because this is actually what you're left with. So I'm talking about that one. So this is t minus 0. And then you have t minus t. And that yields, of course, 0 in total, right? So this is basically what the expectation of this part was. And now I'm going to come back to the variance of the expression. So then you would get rid of the squares. I'm going to address the variance of the squares first. Now that is not a straightforward issue, but the variance of a random variable, okay, no matter what that is the expectation of the squares minus the square of the expectations. That is still true. Now if you replace the random variable by the square of another, which I would need to do it here, right? Then this is what you're going to end up with. So you have the variance of the squares being equal to the expectation of the square to the second, which is the expectation of the random variable to the fourth. So that's going to be the so-called fourth moment of the random variable, which you're about to see. I'm going to write it down a little bit more structured way, so you can see this over here. So again, the variance of a square is equal to the expectation of the fourth moment, which is a fourth moment of the random variable, minus the square of the expectation of the square. Okay? So you would need to break it down. And yeah, so I'm going to basically address that first. So this is, again, the fourth moment of the increments of the Wiener process, sorry. I'm going to come back to that later on, so how to find the fourth moment of the increments of the Wiener process. I'm going to use the normality of the Wiener process, so based on that, it's not going to be that big of a deal as it sounds. And then I will address the expectation of the square of the expectation of the squares, right? And I'm talking about basically the squares of the increments of the Wiener process. Now, okay, how to address the fourth moment? I'm going to use the normality because the fourth moment of the normal distribution is known. So let me just basically address this issue. First off, again, the expectation of the fourth moment is going to be addressed here. And for that, I'm going to use the fact that if a random variable follows the normal distribution with mean mu and variance sigma squared, it's not directly linked to the Wiener process, but it will basically address this issue. Then the fourth moment of the random variable, which is, what is the fourth? The fourth centralized moment, the fourth centralized moment, which is basically the fourth moment of the standardized normal variable. Okay, so x minus mu by sigma is the standardized version of the random variable, and taking that to the fourth is the expected, okay, you don't need to say the word expectation, but that's going to be the fourth centralized, not just centralized, but standardized moment of the random variable is going to be equal to 3. This is something that you might not be familiar with, but this is what it is, okay? If you're not sure about it, I recommend looking into the integral of that, so you basically, you know, based on the transformation theorem, how to calculate the standardized, fourth moment of the normal distribution, okay, which would basically based on the expectation of that. Now, based on this one, because I would need to take sigma out from this proposition here, this is going to be the square of the variance. So based on that, because the expectation of the Wiener process is 0, so transitioning to basically to the Wiener process, the fourth centralized moment, so I'm going to take it out. This is the fourth centralized moment, is going to be equal to 3 times the square of the variance. I'm going to write it as such. So if you want to take this out, this is going to be the square of the variance. Okay, I'm going to split this part. This is sigma to the fourth. I know that, but it's easier to address it this way because I was already addressing the variance of the Wiener process, right? Or the variance of the increments of the Wiener process already. And then you would need to just square it. And the variance of the Wiener process was simply just, or the increments was equal to just basically the length of the ith subinterval from the partition, so we just need to square it. You don't need to take basically the fourth moment of sigma. All right? So this is, so mind that please when you basically see that one. So what I'm going to say is this: the fourth moment of the increment of the Wiener process is going to be equal to 3 times the square of its variance. I'm talking about the variance of the increments, not the squares, the variance of them, okay? So here I basically did that, okay? All right? So 3 times the square of the variance, not the variance, it's square. And this is how you bypass the fourth moment of the increments of the Wiener process. You understand this, guys? Okay? And then you take care of the last, what is basically the expectation of the square. Here it comes. Now, based on that, because I didn't stop here, check this out. Okay, so I don't need the normality basically of the Wiener process anymore. Minus, and then what? Minus the square of the expectation of the square. And what is the expectation of the square? The expectation of the square is going to be the variance plus the square of the expectation. Okay? And that is need to be basically taken to the second. So I'm going to simplify that. This is going to be the square, check it out, the square of the variance plus inside, okay, so the total square, or the whole square, right, plus the actually the expectation, the square of the expectation. And that's it. So this is how I'm breaking it down all the time. Okay, so this is what I need. And that is going to be the square of a variance because the expectation is going to be 0. Okay, so you have 3 times the square of the variance plus minus the square of the variance is going to be 2 times the square of the variance. Just saying, okay? But that's what you're going to see afterwards. All right, let me explain. So here you have minus the square of the variance of the increments, right? I was addressing the variance of the increments before. That was basically just the length of the ith subinterval of the partition. And then you have plus the square of the expectation. Now the expectation was 0 of the increment, so its squared is also going to be 0. But that's that. Okay, so I was basically writing it down like this. Now here again, okay, I'm going to take care of that first. The expectation was 0. Okay, so I'm going to basically put that in. And then, of course, you can ignore it because if you have plus 0 somewhere, just who cares? So you have 3 times the variance, the square of the variance of the increments of the Wiener process, minus 1 times the square of the variance of the same thing is going to be equal to 2 times the square of the variance, right? So simply this is how you basically break it down. So that's going to be, this is interesting, right? So the variance of the squares is going to be 2 times the square of the variance. Okay, in this case. I wasn't expecting that either, but this is basically how it was. Okay, again, but I was using normality for that. So that was the variance of the squares. You got that? Okay. I would basically, this has wild applications in finance though. Okay, and what was the variance of the increments of the Wiener process? The variance was simply just the length of the ith subinterval from the partition, and then you would need to square it. Okay? All right, do you remember on this stuff, guys? Okay, so keep that in mind when I basically address the variance of the sum. Now, why is it important for the Wiener process to have independent increments? One of the reasons is because the variance of the sum will become the sum of the variances. Due to independency, there is no correlation. And if there is no autocorrelation, of course, then of course, you would need to have that, okay, the increments are independent from each other. I mean, I'm talking about the autocorrelation of the, correlation of the independence anyways. So you can simply just bypass actually the variance separated by the sum, which I do. And thank God, I mean, you might ask yourself, okay, where is t at? And the answer is the variance does not depend on additive constants, right? So you can simply just take it out from the variance separator without basically replacing it. And because there is no variance regarding it. Okay, so if you increase the random variable or decrease the random variable by t, you also would decrease the expectation of it. But that's that. So here, this equality, okay, this one, holds because the increments of the random walk, sorry, not the random walk, but of that too, but the Wiener process, sorry, are independent. Okay? And yeah, by definition, by the way. And so I'm going to replace the variance of the squares of the increments, which was, as we have found, 2 times the square of the distance of the ith subinterval of the partition. And then, of course, if you, I mean, you could take 2 out from the sum, which I did, okay? And that is going to be, and this is what simply say 2 times actually the quadratic variation of the identity, which is, again, 0, right? We talked about that. So we'll simply just saw it as basically that this thing, check this out, is converging to 0. That was the main statement, which I did, okay? Why is this true? Okay, we were talked about it. Because the total variation was finite, right? So the total variation, remember that, of the identity. So the quadratic variation would be 0 then. Yeah, Okay. And why is that? Because why is the total variation finite? Because check it out. This, okay, as you see, I mean, here you see it, is a strictly increasing sequence, by the way. So that is, no matter what, this is always true, right? So that's strictly increasing. So that function, the identity function, is actually strictly increasing. That is the reason. Okay, we were showing that one. So why this is true, we were showing that on the previous part. Okay, where we're not even discuss stochastic processes anymore. So to sum it up, okay, again, so which is basically what the summary here is, the variance of this expression, which I would just simply write it down again. So I'm going to use it, as you see, the variance of this expression plus the expectation of the square of the expression. I have found the following things. Okay, so you see that basically here as follows. Okay, we're looking at it. We obtained the following. This was equal to 0. It was equal to 0, and that was converging to 0. So this thing will converge to 0 too. That's it. So the expectation of the squared distance of the random variable to the limit, the mean square limit, right, will converge to 0. And this is basically mean square convergence by definition. Yeah, all right. Okay, so again, let me recall it. So that was converging to 0 at least, and the other one was equal to 0. So this expression, on the right-hand side, was equal to 0. So the whole thing, which is equal to the sum of the two, will converge to 0 as well, which is not a big deal, right? Now, the implication on that is that the mean square limit of this random variable is going to be equal to t. Because what you see here on this side is the expectation of the square distance of the random variable to the limit. And yeah, so here it is. That's basically the final result. So that means that t is the quadratic variation of the Wiener process. I'm going to summarize it basically a little bit more structured way, but that was the major result. So t is the quadratic variation of the Wiener process. Here it is. Okay, so to sum it up, the limit of that expression, which is the sum of the squared increments of the Wiener process, is converging in mean square to t, which is, again, I mean, okay, you can use that symbolic notation as I introduced you to. Again, so that was, okay, I don't want to be arrogant, but that was my idea to give that, basically that expression. This is equal to t, right? We have found it. So that could be actually one of your tasks in the exam to get that, right? That expression, the quadratic variation of the Wiener process, which I just did. Okay? And since this is finite, of course, which we assume that again, so this is a bounded interval to be assumed, so it is finite, then the absolute variation, or you can call it the total variation of the Wiener process, will diverge. So as you split basically a partition of the Wiener process and you increase the number of points, right, for the split, you find that the total variation of the Wiener process would diverge, which is very interesting, right, in that regard. Okay, so if you calculate the length of the paths, the total length of the paths, which is the total variation of the process, you find that it's not going to be finite. Yeah, it is, but it is. Okay, so that was basically one of the major results of today. Okay, now in the last half an hour, I'm going to basically address the Itô integral, which addresses actually, I mean, when you look at the Riemann-Stieltjes integral of the stochastic version of the Riemann-Stieltjes integral, that was a deterministic function, which I'm going to replace by another stochastic process. So you have the same partition and everything else will be the same. Now this time, check this out, we're going to have two stochastic processes, x and y. And y will be the increments, okay, which I'm going to look at, and x will be actually the other process, developing process, you can say. So you have two stochastic processes this time. And now I'm also addressing the mean square limit of the following expression. So as you see, we'll have mean square limits here when I'm looking at the Itô integral. I'm not Japanese, so basically I don't know how to pronounce it. I tried to look it up, but the correct pronunciation was, I thought, Itô, okay? Some people say Itô, but I think it's not correct. So Itô was probably the right way to pronounce it. Now, in this case, I want to basically want you to note something. Notice that in this case, though, that will not be some point between the lower and the upper endpoint of the ith subinterval from the partition. That will be the lower endpoint of the partition. So that is not going to be Si asterisk, that is going to be Si minus 1. Okay, so keep that in mind. This is very important. This is the lower endpoint of the ith subinterval of the partition. It will stay the lower endpoint. So you cannot change that. This is very important. Okay, because when it comes to the other integral, you will need to define it differently. All right? Now, okay, you're going to look at the increments of the other process, okay, as you see. So just to remind you, Si minus 1 is not, in this case, Si asterisk. So you cannot transition the Riemann-Stieltjes integral directly to the Itô integral. These are two different things. Because when we were addressing the Riemann-Stieltjes integral for deterministic functions, this point was somewhere between Si minus 1 and Si. But now it must be at the lower endpoint, otherwise it doesn't work. And I'm going to look at the mean square limit of that. Okay, and the mean square limit of that will be the Itô integral. Now, in finance, it's very typical. Okay, so this is basically the random change, okay, let's say of a price, okay, and then you have basically there's some future change in the price with the current value, okay, and you sum it up, that will basically generate some profit. So this is very important and very common one when it comes to financial calculus regarding it. Okay, so the Itô integral is a major, the most common one, because again, that, addresses some future values or future increments at a given point of time. Okay, so some future growth basically. If it's in the middle, then you're basically not sure how it will evolve. Anyway, so the mean square limit of this thing, which is going to be the Itô integral, and let me just write it down. So it is going to be the integral from 0 to t, in this case, without loss of generality, so that was most of the time a to b, but the lower endpoint of the interval of the basic on which I'm integrating is 0, without loss of generality, and the upper endpoint is supposed to be t by now. I'm going to write it like this, so xs, of course, but what I'm going to do is I'm going to write down a minus here. The minus basically should remind you on the fact that you would need to look at the lower endpoint of the ith subinterval of the partition and not somewhere in the middle. Okay, because if you look in the middle, that this is going to be different. Okay? Pardon? No, it's a lower endpoint. It cannot be the upper endpoint. It cannot be, because that's not the Itô integral then. So the mean square limit of this thing that you were defining, maybe I'm going to create an exercise based on that. So what would be the upper, right, if you replace the lower endpoint by the upper endpoint? This is not the Itô integral. Okay? So this is not very common that people write it like this. Okay? So in the middle sign, but I find it's very substantial, because then you don't understand what the Itô integral is actually. And I want you to understand it. So the meaning of that minus sign is that when it comes to this process x, which we are integrating, of course, with respect to y. So we're integrating x with respect to y. We shall, and this is something which you remind you of, we shall look at the lower endpoints of the subintervals, and only the lower endpoints of the subintervals, and not the upper endpoints of the subintervals. You understand the point, guys? Okay? And that's very important, and I want to stress this. I cannot stress this enough. So that's the most important part here in this expression. All right? Now the mean square limit of the whole thing is going to be actually the Itô integral of the stochastic process x with respect to the other stochastic process y. Okay? And I want you to stress, because this is something that you ask here, if you take the upper endpoint, that's not going to be the Itô integral. So you must take the lower endpoint. Okay? And that's why I use, again, so this is just me. You don't need to. But I use basically this expression regarding the Itô integral. And I'm going to use that across the board, even when considering stochastic differential equations, which is going to be based on the Itô integrals and not on other integrals, especially with respect to the Wiener process. Anyway, okay, so that's that. Okay, so that is basically the issue. Keep that in mind. It's very important. I cannot stress how important this is. Okay? It must be the lower endpoint, and it cannot be anything else. If it's something else, then it's going to be a different integral. There is also another one, and that's why I was introduced to it. But that's not common in finance. Because again, we only know basically at the current point of time, but we doesn't know what happens in the future. Okay? But when you're basically, if we know what happens basically after that, we can use the Stratonovich integral, which behaves more like the Riemann integral or the Riemann-Stieltjes integral rather than the Itô integral. In this case, the endpoint is going to be in the middle of actually of SI and SI minus 1. This generates some sort of a trapezoid when you look at the sum. Okay, so if you take that, this is basically generating some sort of a trapezoid. Okay, so if this is, let's say, the Riemann sum, I mean, it's not, but if it was, okay? And I'm going to make that as an example. This is not directly linked to stochastic integrals, but you should understand what actually the Stratonovich integral does. So when you, let's say, take a function, okay? And you would calculate the Stratonovich integral of the function, which is also, if the function is continuous, that would be the Riemann integral as well, okay? But let's say you got the partition here, S, and the lower endpoint SI, and then you got SI minus 1 and SI between those two. Okay, so that would be basically partition between those two, okay? What you're doing here, and I want to basically calculate SI minus 1 times, okay, so I'm going to multiply that, times the function at the middle point of that, which will be here, okay? So that will be somewhere in the middle between the two. So this is the middle point here, right? This is in the middle, right? So this is SI plus SI minus 1 divided by 2, and then you take this value for it, okay? Which will be, okay, so when you look at that, so the length of this rectangle here in the middle, this will be equal, okay, so the area of the dark blue one, which I'm going to fix here, which is corresponding to it, you see, is going to be equal to the area of this trapezoid, you see? So the light blue trapezoid, I cannot basically turn it away. So the area of the dark blue rectangle, okay, is going to be equal to the light blue trapezoid. I'm not sure if you see it. I didn't do it very well. Maybe I'm trying it again. I'm not sure if I can make it, but maybe I'm trying to do it again. Okay, so you see basically what the point is. I hope I'm not going to fail. Okay, so here is the function. Okay, so basically what I'm saying is that in the Riemann sense, so I'm not basically looking at the Stratonovich because that is linked to stochastic processes, but if the functions were deterministic, so let's say y is equal to the identity and g is some deterministic function, okay? And here you got SI, and here you have, SI minus 1, and here you have SI, right? Actually, what you're doing here, okay, this expression, is the area of the trapezoid. Here, this one. Okay? And that will also converge to the limit of the Riemann sum. So basically, in the Riemann sense, it doesn't matter because It doesn't matter which point you take, basically, whether you take it in the middle or you take basically the upper end point or the lower end point, it doesn't really matter. But if you take it in the middle, then you're generating basically the Stratonovich integral, and in the stochastic sense, that is called the Stratonovich integral. You understand the point? There is going to be a difference between the Itô integral and the Stratonovich integral, because in case of stochastic processes, it is going to be important whether you take the lower end point or the middle or the upper end point or even something else. Okay? So, but by definition, this is going to be the Stratonovich integral, and that is going to be expressed by a little circle in the middle between the function that you're integrating and d, which is a differential operator, and then you have basically the integrator. You understand the point? Okay, and that is important. Okay, so this is, again, this is different, so people want to distinguish between the two, but these are the most common ones when it comes to stochastic integrals, where both the integrator as well as the integrand are stochastic processes. Okay, and these are the major two. You understand the point, guys? Okay, so in this case, it's Stratonovich. You can link that basically to the trapezoid if or the area of a trapezoid in the Riemann sense, if you're looking at the Riemann sense. But again, regarding the Riemann sum will converge to the same limit as, again, so for specific functions, basically as, you know, the Stratonovich analog of it. Okay, so whether you take the middle point or the upper end point or the lower end point for basically for the from the sub intervals, it doesn't matter in the Riemann sense, but it does matter when basically you're integrating stochastic processes where both the integrand as well as the integrator are stochastic. That was not the case for the Riemann stochastic integral as well as the stochastic Riemann-Stieltjes integral, because for the Riemann stochastic integral, the function was the integrand was stochastic, but the integrator was deterministic. And for this, in the Stieltjes sense, the integrator was stochastic and the integrand was deterministic. But here are both stochastic, and that blows away. So the transition here is not going to work very well when you transition from the Riemann-Stieltjes context to basically the stochastic version, where both the integrand as well as the integrator are stochastic. So that's not going to be the same. Okay. Now I'm going to show. So I'm going to go back to the Itô version, and again, in case of the Itô version, I write it like this. And even if I write stochastic differential equations, okay, so making sure that is based on Itô calculus, not the Stratonovich calculus, the Itô calculus. Okay. So most people don't do that. I will. Okay, because I find it very important that you look at that from the Itô sense. Okay, now, so I'm going to look at the Itô integral of Wiener processes. So both the integrand as well as the integrator are going to be Wiener processes now. And I'm going to show you that this integral, what you see, again, this is the Itô integral of the Wiener process, is going to be equal to 1/2 times the difference of the square of the Wiener process at time point t minus t. And if you ask me why this is, okay, then my answer to that will be that the reason why this is because the quadratic variation of the Wiener process is finite. That's the answer. I'm going to show you that, okay? So that this is basically explaining t, where t is coming from. Just to give you a little comparison. So when it comes to regular functions, guys, okay, because you might not see this. Okay, if I look at the integral of x, okay, with respect to x, so both the integrand as well as the integrator are x's, right? And I'm going to look at that one from 0 to t. No stochastic processes, everything is deterministic, whatever. You see? What is going to be? Now, of course, you need to find, according to the Riemann, the fundamental theorem of calculus is claiming that this is going to be the antiderivative of the function x, which is at point, you can take any of them, but you would need to basically be more specific in that regard. This is going to be 1/2 times x squared plus c, right? So, but you could skip plus c in this sense. Okay, so that would be actually, and of course, if you look at that point, you would put in t and then 0, we subtract the 2, so that would be basically, that would be 1/2 times t squared would be actually the Riemann integral of x with respect to x, you see? So, and that is quite the same as here in this case, but here comes minus t also. And the question is why, and the answer is because of the quadratic variation of the Wiener process. That's the reason. Because t was the quadratic variation of the Wiener process, okay? So one cannot simply just, look at the antiderivative of the Wiener process because there is no antiderivative of the Wiener process in this case. So you need to address this issue differently, and this is what I'm going to do in the remainder of this lecture. So we're going to prove it. It's not difficult. Okay, so after that, maybe you can try what happens if you take the upper limit instead of the lower limit. Because for the Itô calculus is explicitly addressing that you should take the lower limit, basically, of your integrand when you look at the limit of the mean square limit of the sum. And it's always going to be the mean square limit, by the way. So this is something which people tend to neglect all the time, which I don't find very appropriate. So again, in this case, you can write it like this. But keep that in mind. This is the mean square limit of of this expression. All right. So what happens if you take the upper limit? You can maybe check that out as a homework if you like to. I'm going to look at the. I'm going to prove that statement. We have done this before, but we've done that, but not, you don't see it directly. So I want to basically, we've done this indirectly because I was already addressing the quadratic variation of the Wiener process, and here comes it back again. And that's the point. Okay, so when you look at that, okay, 1/2, okay, this is just a trick. So where is 1/2 is coming from? Don't worry about it, you're going to see. Because 1/2 times 2 is going to be 1. Okay, so that will be disappearing. I'm going to write it down like this, so you see 2 times the sum here, where I would multiply w, so the orange version, at point si minus 1 with basically the upper, you can call it the upper value if you like, of the Wiener process. So the Wiener process at the upper end point of the interval. So the orange one times the purple one. Check it out. Okay. And then you multiply the orange one times this purple one, which is identical. So you take the square of the orange one, which would be actually the square of the Wiener process for the lower end point. Okay, so I was still writing it down in purple because here I was writing down the integrator in purple, or the increments basically on that. But I'm changing the color. Check it out. So this is going to change because these two are equal. Okay, so I'm going to make it orange again. All right, so don't basically mix it up. If you, and let me basically stress this, if you look at the upper limit, you're going to see something else. Okay, it's not that different. Okay, so this is going to be staying there, but the other expression, again, so this is going to be, you have basically the product of the upper limits after all. That's going to be a little different. But anyway, you can try it out, so I'm basically excited what you will see later on after that. Anyways, now, I'm going to, what you might ask, okay, why I'm doing this basically with 1/2 times 2 shit, because, okay, that would be redundant. So even if I didn't do it, then let me just basically make that quick. Okay, so make that observation quick. That will still be true, okay? So that would be, maybe I should have done this presentation like that, so then that would be still be true, you see? So where does it basically 1/2 times 2 shit comes from, sorry, but that will be basically explained later on. Okay, so don't worry about it, because this, but that's, you should see that it doesn't change anything. So if you multiply something by 2 and then multiply it by 1/2, it's not going to change. Okay? Good. Now, okay, I'm going to express this a little bit where basically the quadratic variation is going to be apparent at some point. Now, I'll make use of the fact that b² minus a², which will resemble to the expressions here that you're about to see, minus the square of b minus a, which is addressed by the binomial formula. Okay, so first I'm going to take that. Again, you might not know where basically what I was using this for, but you will. You should trust me on this. It's going to be apparent. Okay, so first I'm going to write that down, b squared minus I squared. That's not a big deal. Okay, so b squared minus I squared, and then minus. Okay, and then I'm going to break that down. This is b squared minus 2 times a times b plus a squared, and since it's minus in front of it, this becomes minus b squared plus 2 times a times b, and then minus a squared. You might ask yourself why I'm doing that, but again, I'm going to come back to your issues. Don't worry. And then, of course, what you see here is that b squared is going to be canceled, and then you have minus 2 times a squared. So this is going to be 2 times a times b minus 2 times a squared. Okay? Because you have minus a squared equals 2 times a squared, minus 2 times a squared. You see that? Okay? Now, you might not know why I'm doing that or why I did it, but the reason why I did it, check it out, is because this expression resembles to that. You should basically just ignore the sum operator. You can take that with you. So I will let you take it with you, okay? But there is, if you just simply ignore the sum operator, you simply find it again. You see? So this means that since this is equal to that, okay, you can change it. Okay? You see? So you can see what this is going to become. Check it out. I was using colors for the presentation. So the yellow expression here that you see, check it out, is resembling to this expression without the sum. Okay, so if you didn't have the sum there, it would be the same. Okay? The green one is resembling to that, you see? So since this is equal to this one, the structure will be kept if you just simply just switch it. So what I'm going to do now is I'm going to change that. So it's going to be 1/2 times the parentheses, which is going to stay. So I keep the brackets. I don't change the brackets again. And then after that, okay, this is the blue one. So this is b squared minus a squared. Now b corresponds to the upper endpoint, you see? And that's why I did it in orange, so that colors will help. And a will correspond to the lower endpoint. So that's going to be the square of the upper endpoint minus the square of the lower endpoint. And then you take the sum with you, and the 2 is not there anymore. Check it out. So in blue, check it out, 2 times, okay, the 2 disappeared. So you have the sum from the first to the last. So then I'm going to start with b squared. B squared is the Wiener process, the square of the Wiener process at the upper endpoint of the ith subinterval, and then you have minus the square of the Wiener process at the lower endpoint of the subinterval. You see that? Okay, so that's the same. And then minus what? And check this out. What is that? Actually, that resembles to the quadratic, or the quadratic variation is going to be apparent, but here it's going to come. So the limit of the purple expression, which is the square of the upper endpoint minus the Wiener process at the upper endpoint minus the Wiener process at the lower endpoint of the process. Okay, you see? The limit of the pink expression, not purple, sorry, is going to be the quadratic variation of the Wiener process, which is going to, again, which is going to be t. We did that, so we don't need to do it again. You see? So this thing, okay, now this is actually here, okay? You can see that over here, that one. Okay, and check it out, the pink expression, the pink one, the limit of the pink, the mean square limit of the pink expression is equal to t because t is the quadratic variation of the Wiener process. And the quadratic variation of the Wiener process is the limit of this expression. Okay, here it is. So as, of course, n, which is, you know, the number of points from the partition is tending to infinity. You see? And that is why you have 1/2 times the square of the Wiener process at time point t. This is actually, I didn't forget it, but by definition, this is equal to 0 almost surely. Right? Okay? And that is, of course, okay, the final one, which would be actually the mean square limit of that. The final one would be just simply 1/2 times the square of the Wiener process at time point t minus t, right? That's it. You see? That is it. So that is the limit. Okay? You understand it now, guys? So the answer why the Itô integral is the way it is because I told you before, the quadratic variation of the Wiener process is finite. Not just finite, but greater than 0. Okay? And that comes with the Itô integral as well as Itô's lemma and all that stuff. Okay? All right? Well, this is actually by far the longest presentation that I did. So regarding basically the number of slides which crashed, so it has 2,200 pages, but of course this is not the handout that you were given to. Okay, but that was the reason why I crashed my computer based on that, because it got too big. So I was splitting it, this part. But that was a lesson to learn. Pardon?
How large was it? Was it 5?
That was a very big one. Almost like 600 megabytes or something. You know, which a PowerPoint file, which is too big. So, I had a lot of elements in it. So that was the reason why I had to cancel last week's lecture, unfortunately. But I wasn't aware. Okay, that PowerPoint cannot deal with that. So if you're doing a presentation like this where then of course you have those effects and all that stuff, it's going to be too big. Anyway, but that was it. So I had to repair my whole presentation. So I was starting at 0, and that was a lot of work. So that's why I needed to cancel it. Okay, guys. We're gonna have a lecture next week, of course, right? And I tried to set up another lecture in parallel, which I will post as a video. So you were telling me that it would not be an issue for you if you watch it as a video. So, but that will be a shorter one. So because I don't like the videos, so I'm doing those videos all the time, but I don't like them. I have to admit. Okay, it's actually much better if you come here and actively trying to think the video. But you can back it up, so you can watch it. Maybe you didn't understand something, you can check it out then. Okay, guys, that was it for today, and see you next week, of course. Take care.